Okay, so we want to continue our discussion of the implicit function theorem. Let me remind you of what the theorem says. So assume that we have some two-variable function, which we called capital F. It's very important to distinguish in your notes between small f's and big F's, either by making the small f's curlier and the big F's more square, or by, in terms of size or font or whatever. So big F is a function of x and y. It's a C1 function, namely it has a continuous partial derivatives in a neighborhood of some point x0, y0. This is the relation between x and y, which is not necessarily given as in terms of y as a function of x. And we want to know, can we express y as a function of x locally? Is there near a point? Can we express y as a function of x? That's the issue we're addressing in this theorem and in this discussion. So our assumption is, first of all, that x0, y0, when you apply the relation to it, you get 0. That just means that this point is one of the points on the curve that this relation is prescribing. And the second assumption is that at that point, the derivative does not vanish with respect to the second variable, with respect to y. Okay? And we demonstrated in an example why these two conditions precisely tell us that we're looking at a point, not just a general point in the plane, but a point at which we're interested to express y as a function of x, and why that point is nothing bad happens. Okay? Remember the example with a circle that we discussed? Okay. And the theorem says, then there is a unique function, y equals f of x. This unique function is the implicit function. The theorem does not give you a formula. It just says there is a unique function, y equals f of x. It's going to be a C1 function with continuous partial derivatives in a neighborhood of x0, such that f of x0 equals y0. Moreover, if you take f of x and plug it in for y here, you're going to get 0, meaning that all these points of the form y equals f of x precisely satisfy the relation, so that this function y equals f of x is saying the same thing as f of xy equals 0, but in terms of a function. Okay? This condition 2 is the one that says in the most precise way that writing y equals f of x, or writing the relation f of xy equals 0, gives you the same thing. Do you see that? Okay, you plug in f of x for y, you get 0. So y equals f of x satisfies f of xy equals 0, satisfies the relation. And finally, there's this further result saying that you can find the derivative of this function, although you don't know a formula for it, in terms of the partial derivatives. There's no minus here, this is a mistake. In terms of the partial derivatives of the original relation f, and note that we're assuming that it doesn't vanish, therefore we can divide by it, the partial with respect to y. Okay, so this is the theorem. What I want to do, the first thing I want to do is generalize this theorem. Generalize it to, we're going to generalize it in steps. So the first step of the generalization is going to be, I want to assume now that we don't have just two variables, but we're going to have some more of them. Okay? So instead of x and y, I'm going to write, well, I don't know how many, so I can't just write x, y, z, because that's it, I'm out of letters. So I'm going to write x1, x2, x3, x4, x5, etc., and in general xn. And there's going to be a one variable that I'm going to still call y, because that's the one that I want to write as a function of all the other variables. Okay? So let's see. I already wrote it on another board. I want you to look at this, kind of remember what this looks like, and let's move on to this board and see the generalization. So I'm denoting x to be x1, x2, x up to xn. Okay? So this is now a vector that has n variables. Okay? And now, here's the theorem. Let f be a relation of all these n variables with another n plus first variable y. Okay, I'm not including it here just because I want to highlight it. There's a different statement about this y. And we're assuming again that it's a C1 function in a neighborhood of some point n0, which again is a point that has n plus 1 coordinates. Okay, so maybe the zeros should have been up here, but never mind. N plus 1 coordinates. The first n coordinates are x coordinates, and then there's this other y coordinate. Such that at the point the relation is 0, and the derivative with respect to the special variable at the point is not 0. Okay? Then there exists a unique function, y equals f of x, so I can write that special variable as a function of all the other variables. Okay? It's going to, again, be a C1 function in a neighborhood of x0, of all those n coordinates, such that y0 is f of x0. When you plug in this into y, it satisfies the relation. This just means that this is a function representation of the relation. This is an implicit function. The relation near the point is given by an implicit function. And finally, we have formulas for the derivatives. And note that now f is a function of n variables, so we can discuss n partial derivatives, df to dxi, where I ranges from 1 to n, right? Because f is a function of n variables. X is x1 up to xn. Good, everybody with me? Okay, so each one is given by the derivative of capital F with respect to that specific variable, divided by the derivative of f with respect to that specific variable y that we singled out. Okay, and there's a minus up here. So it does fill up an entire board. Let's do an example. Okay, see that there's nothing scary about this, and everything actually is very straightforward here. Okay, let's do an example. After we do the example, we'll discuss the proof of the theorem, which is not that difficult. It's a rather surprising theorem if you think about it. Okay, we're not used to seeing theorems that tell you, hey, there is something very general out there which you know exists, and you can even take derivatives of, but you don't know a formula for it. Okay, it's a theorem that takes time to get used to. So here's our example. Let's look at the equation 3x squared y minus yz squared minus 4xz minus 7 equals 0. 3x squared y minus yz squared minus 4xz minus 7 equals 0. Okay, and I want to show, we will show that near meaning in a neighborhood of the point negative 1, 1, 2, we can write y as a function of the other two variables, x and z. We can write y as a function of the variables x and z. And so this we will show, and we will find df to dx at that point. Negative 1, 2. F is a function of x and z, and I want to find its the value of the partial with respect to x at the point negative 1, 2. That's the x and the z. Okay, so how do I do this? Well, of course I want to use the theorem. Okay, it's not, and we'll remark in a second that actually in this case we can do it without the theorem, and that's on purpose. That's so we can verify our result according to the theorem. So let's do it. So first of all, I have to fit everything into the framework of the theorem, right? That's how we use a theorem. So I have to write the relation f of x, y, z, set it equal to 0, right? I'm just putting everything into the framework of the relation. So what is f of x, y, z going to be? It's just going to be this. Do you agree? So f of x, y, z is going to be 3x squared y minus yz squared minus 4xz minus 7. Do you agree? Okay. The first thing we have to verify is that this function of three variables is C1, has continuous partial derivatives, and that's obvious because this is a polynomial in three variables. Do you agree? So this is a C1 function. It's C1 on the entire, everywhere in R3, so no careful discussion is required here. Okay, what's the point n0 in which we're interested? That's this point. So n0 is going to be the point -1, 1, 2. Good? Okay, the first thing that we have to check is, does this point satisfy the relation? Namely, if you plug in the point, do you get 0? Okay, so let's see that. F at the point -1, 1, 2 is what? I have to plug in -1 for x, so I get 3 here times 1, so this is 3, minus y times z squared, so this is 4, y is 1, so it's 3 minus 4, so far I'm at -1. X times z is -1 times 2, it's -2, minus 4 times -2 is 8, so I'm at -1 plus 8, minus 7, I get 0. Did everybody follow? That was hard, right? Good. I like it when sometimes people say, yeah, this was easy, I actually got it. Good. Good? Everybody? Okay. Now we have to check the derivative with respect to the variable we're interested in, and the variable is y, right? We want to write y as a function of the other two variables. And does it matter that the other two variables are sitting on both sides of y rather than x1, x2, x3, y? It doesn't matter, of course. Okay? So let's check that. What is the derivative of f with respect to y? So the derivative of f with respect to y is 3x squared minus z squared. That's it. Do you agree? And now we have to check that the derivative, so this was just calculating it, but what we have to verify is that this derivative at the point does not vanish. So what's this derivative at this point n0? Note that the derivative in general is a function of all three variables, right? In this case, it doesn't have y's in it, so at this point it's -1 squared is 1, so it's 3, minus 2 squared, minus 4, so this derivative is just -1, and in particular, it's non-zero. Do you agree? Okay, so glancing back at the theorem over here, we just verified up to here that all the conditions are satisfied. Please look at this board. Hello, over here. Thank you. We just verified that all the conditions are satisfied. The function, the relation we defined, is a C1 function. At the point we're interested in, it's 0. However, the derivative with respect to the variable that we want to single as a function of the other variables is not 0 at the point. Everybody good? Okay. Now let's see what the conclusions tell us. Then there exists a unique function, y equals f of the other variables, right? So the other variables in our case are x and z. So we know now that there is a function that we can write y equals f of xz. It's going to be a smooth function, a C1 function. It's going to satisfy this, satisfy the relation, and it's going to have the derivatives given by these formulas. Okay, so let's write that. So by the theorem, so our conclusion by the theorem, according to the theorem, the implicit function theorem, in this case the three-variable version of it, there exists y equals f of x and z, which is a C1 function near the point we're interested in. X was -1 and z was 2, in the neighborhood of this. So that's the first thing we said we will show. We said we will show that we can write y as a function of x and z. We just showed it. The theorem tells us we can do it. We didn't give a formula, but we can't give a formula if what we're using is the theorem. Okay? The theorem doesn't give us a formula. It just says it exists. So according to the theorem, we showed it. Is it clear so far? Okay? But furthermore, we said we will find the derivative. So now let's calculate, calculating, what did we want to calculate? The derivative of f with respect to x at this point. So how do we do it? The theorem tells us that we need to calculate the derivative of f with respect to x. That's going to be the numerator. And we need to calculate the derivative of f with respect to y, and we need to divide them. Okay? So what's the derivative of f with respect to x? F was that relation 3x squared y minus yz squared minus 4xz minus 7, remember? Its derivative with respect to x is what? It's 6xy minus 4z. Do you agree? Everybody? And the derivative with respect to y, let's write this in a second. So in particular, what's the derivative with respect to x? Okay, let's do both. So the derivative with respect to y, we already calculated in the previous board in order to verify that it's non-zero, remember? So the derivative with respect to y was 3x squared minus z squared. Good? And therefore, the theorem tells us that the derivative of f, of the implicit function with respect to x at the point minus 1, 2, equals minus the derivative with respect to x, 6xy minus 4z, divided by the derivative with respect to y, 3x squared minus z squared, right? And all of this has to be evaluated at the point, which point? At the point, where's f? F is not here any longer. At the point xz, f of xz. Okay, at the point xz, f of xz. Okay, let's look back at here I wrote it in full detail in this original version of the theorem. We're evaluating these derivatives at the point x, f of x. So when we have f of x, y, z at the point x, f of y, z, or in that case it was x, z, f of y, z, f of x, z for y. Is it clear, or did I just confuse everybody? I confused everybody. Let's add it over here, okay? Here's the three variable version. Let's add it over here. We evaluate this at the point x, f of x. That's and likewise for the bottom. X, f of x. Okay, x are all the variables. X are all the variables that we that are still variables, and f of x is now the function that special variable is a function of all the others. Clear? Yes. You're looking at this board? Okay, let's move back to this board. So what are you asking? Plus, right, because it's minus this entire thing. Thank you very much. Good. Okay, so we have to evaluate this at the point -1, and I'm going to write it as -1, 1, 2, because the y was the variable sitting in the middle. Okay, so I'm going to write it like this. And note that, of course, f of -1, 2 is 1. That was the first statement of the theorem, that y0 is f of x0, right? So if this was x0, then y of it is going to be precisely y0. Good? Okay, so what do we get? Now it's just plugging in numbers. Negative 1 times 1, so we get a 6 here, plus 8, so we get 14, divided by negative 1 squared, so we get 3 minus 4 by negative 1, so we get minus 14. Clear? Yes?
Are we always going to find y in terms of the other variable? Like, can we find z in terms of that?
Yeah, so in this example, I asked you to find y in terms of the other variables, which in this case were x and z. The theorem, of course, the fact that I'm calling one of the variables by a special name over here, I'm calling it y, it's just to kind of clarify that this is the variable that I want to write as a function of the other variables, okay? But this is completely general. If your variables are called x, y, z, you can write z as a function of x and y, or x as a function of y and z, or any way you want it. You just have to verify that you're looking at the conditions and the results accurately, according to what you chose. So if the variable you want to set as a function of the others, for example, if you want to write z as a function of x and y, then the derivative that you have to check that doesn't vanish is the derivative with respect to z. Okay? And in these formulas, you're going to have the derivative with respect to z here, and the other two are the ones you're interested in. Okay? We'll do it in this example. Okay? I plan to do it anyway. So let's do that. So let's pause a second before we do that. So up to here, note that we guarantee by the theorem, abstractly, that there exists a function and found the derivative using the formula given by the theorem, without knowing the formula for the function. Do you agree? What I want to show you now is that in this example, we can actually write the function explicitly. Okay, so let's do that a second and find its derivative at that point and see that it's indeed minus 14, just to see that everything we did actually fits in with, in this case, we can actually find the function explicitly. We don't need the theorem. Okay, so let's do that. I just have to figure out what I want to erase. So let's erase over here. So this was our original relation. Let's show that in fact, in this specific example, we didn't need the implicit function theorem. Okay, so in fact, can we write y as a function of x and z in this example? It's rather easy, right? So how do we do it? We write 3x squared y minus yz squared equals 4xz plus 7. And therefore, we can pull out a y here. Y times 3x squared minus z squared equals 4xz plus 7. And y equals, there it is, 4xz plus 7 divided by 3x squared minus z squared. Do you agree? So, without the theorem will never give us a formula, but in this case we can actually extract a concrete, an explicit, not an implicit, an explicit formula for y as a function of x and z. Do you agree? Okay, so in this case, in this example, we can find, can somebody go and close the door over there so that the noise from outside doesn't, thanks. In this example, we can find y equals f of xz explicitly. Without the theorem. Clear? And let's just verify the derivative. So what's the derivative of this thing? Now I still have an issue of what to erase. So I want to find the derivative of y, of this function, with respect to x. It's going to be a product rule. Sorry, a quotient rule. Do you see that? It's going to be a quotient rule, and then I'm going to plug in the value. So let's do it here. And I'll leave the bottom line on the board so we can actually verify that we got precisely the same thing. So let's recall what y was. Y was 4xz minus plus 7 divided by 3x squared minus z squared. So dy, y is f. Let's emphasize that. Y as a function of x and z equals, so the derivative of y, the derivative of f with respect to x is what? So I'm using the quotient rule. So I have 4z times the bottom, 3x squared minus z squared, minus the top, 4xz plus 7, times the derivative of the bottom with respect to x. So it's what, 6x, right? Please verify that I'm not making any stupid mistakes here. Divided by 3x squared minus z squared, all of this squared, right? Okay, and therefore, what's this derivative at -1, 2? I just have to plug in the values. So 2, so I get 8 times 3 minus 4. 3 minus 4 is -1 times 8, I get -8, minus, so there's a 6, -6 here, so let's write it plus, 6 times 4 times -2 is -8 plus 7, so it's -1, so it's a minus again. Sorry about that. So it's minus 6 divided by 3 minus 4, which is -1, squared. So it's 1. So it's -14. Yay. Same thing. Good? Okay. So in this example, we can actually see that what we did here according to the theorem, without knowing the explicit formula for the function, indeed fits in with what we get naively. Okay. I want to comment one more thing, and that's what I mentioned earlier. Suppose we took this exact same example and wanted to write z as a function of x and y. We wrote y as a function of x and z. Let's try to write z as a function of x and y. So again, I'm looking back at the same example. What would happen if I wanted to write z as a function of x and y? Do you agree that explicitly, without using the theorem, I can do it? It's a quadratic equation in the variable z. I can solve it and find z in terms of x and y. Do you agree? So in this example, we can write z equals f of xy explicitly by the quadratic formula. Right? We can solve this thing for z. Does everybody understand what I'm saying? Right? I can solve this for z and get z, or there are going to be two solutions, right? Maybe one of them will be ruled out for some reason, but I'm going to get something of the form, well, providing things turn out nicely. Z equal, maybe I even did this. Yeah. Ooh, turns out ugly, but can be done. Okay? Do you agree? Okay. However, do it. Solve this for z where x and y are parameters and see what you get. Okay? However, the theorem, so what if we try to do that using the theorem? The theorem fails. What does it mean the theorem fails? If I looked at this and said, okay, let's guarantee existence of of an implicit function, z is a function of x and y, according to the theorem, I would have to check the conditions of the theorem, right? And what are the conditions of the theorem? Well, it has to be a f, this thing has to be a C1 function. That's still true, right? It has to satisfy that at the point we were looking at, it's 0, and that was satisfied because it's the same point. I'm looking at the same point. Let's write. The theorem fails at n0, which was the point, oh boy, I forgot. What was it? Negative 1, 1, 2? Was that the point? Okay. But there's another condition. The derivative of f with respect to the variable I'm trying to isolate, to write as a function of the other, cannot vanish. So what's the derivative of f with respect to z? It's what? It's minus 2yz minus 4x. Do you agree? And therefore, the derivative of f with respect to z at the point n0 is what? I'm plugging negative 1 for x, so I get a 4 here, and 1 and 2 for y and z, I get a minus 4 here, I get 0. Do you see that? So the theorem doesn't hold. Okay? So in this case, the theorem doesn't hold. Oops. Okay? So what's the bottom line of this? Why did I mention this? It's important to note what the theorem tells you and what the theorem doesn't tell you. The theorem tells you if conditions A, B, C, and D hold, then there is an implicit function. You can write an implicit function. Furthermore, you know how to find its derivative. If the conditions don't hold, it doesn't tell you that there is no function. It just tells you, hey, I don't know how to do it. Try something else. And in this case, trying something else is just doing it straightforward, the way you would have done it if I would have given you this before we ever discussed the implicit function theorem. Okay? Clear? So that's important to remember. The theorem is not an if and only if statement. If the requirements of the theorem are not satisfied, it doesn't mean that there's no function. It just means that the theorem doesn't apply at that case and you can try something else. Okay? Let me show you another example of that. So this is going to be a very short example. So here's another example. Let's look at the function. Here's the relation. F of xy equals x minus y to the power 3. Can you tell me how to write y as a function of x such that f of xy would equal to 0? So we want to know, can we write y as a function of x such that f of xy equals 0? What can y be? When would this be 0? Y has to be x. There's not much choice. Do you agree? So this is if and only if y equals x. Does everybody agree? And in fact, that goes for both variables. So this equals 0 if and only if y equals x. That means that's how I would write y as a function of x. And in fact, that's how I would write x as a function of y. Right? So this is an explicit function that prescribes this relation at any point. And that's of course, it's unique. Remember, the theorem tells you it's unique, and it's unique here. Good? But what with the theorem? Can I find it using the theorem? Okay, so there is an explicit function at any point. Okay, however, at 0, 0, the theorem won't find it. Okay? what happens at 0, 0? What's the derivative of f with respect to x? The derivative of f with respect to x is 3x minus y squared times the inner derivative, which is 1. Evaluated at 0, 0, it's 0. Do you agree? So if I would try to use the theorem to isolate x as a function of y, the only condition that I have to verify, would fail. Can't do it. The theorem doesn't guarantee anything. And similarly, for the other variable, df to dy at 0, 0 is again 3x minus y squared. Well, actually now there's an inner derivative, which is minus 1, so there's going to be a negative sign here. But again, it's 0, it's just, well, that looks like a 6. It's 0 again. Okay? So the theorem fails again. Well, when I'm saying the theorem fails, it sounds as if the theorem tells you something wrong. That's not what I mean to say, of course. The theorem doesn't apply. Okay, I can't use the theorem here. Clear? So it's important to remember that the theorem is not an if and only if statement. Okay. So in the next I want to discuss question?
Like this is true for every point like 0, 0, 1, 1, 2, 2.
No. The derivative, yes, but at other points, if you look at points of the form x equals y, this would also be true. The theorem would not hold there. But if you look at points of the form, for example, 3, 5, then this would not be 0, and you can use the theorem, the implicit function theorem. Okay, true, yeah. More questions? Okay, so what I want to do next is continue this discussion and prove the theorem. I'm going to only prove the light version, the two-variable version, but the proof is somewhat illuminating, okay? So I want to prove the entire thing, both the existence and the uniqueness of the implicit function, and to derive the formula for the derivative. And both are not hard. So that's coming up next.